Good evening, everyone. Welcome to this lecture. My name's Tony Symes, and I organise the monthly lectures for the Herschel Society. And the title of tonight's lecture is The Chemistry of the Universe, and the lecturer is Professor Mike Edmunds. The Herschel Society holds its lectures here with the support of the Bath Royal Literary and Scientific Institution, and the Society brings together like-minded people who are interested both in modern astronomy and the historical contribution of the extraordinary Herschel family. And so we would welcome new members if you're interested, and we have flyers which will tell you how to join. A bit of housekeeping. Please note that this lecture is being recorded. If you're in the room, if you hear the fire alarm, please proceed down the main staircase where you came in to the ground floor and exit through the front doors, and turn right again. The assembly point is the fenced area at the bottom of Queen Square, known as Chapel Row. If those stairs are impassable, you can go through to the dinosaur room, through that door there, and down through the stairs and out through number 18. The passenger lift must not be used during a fire event, so if you have mobility difficulties, please gather in the stairwell by the lift with the emergency doors closed. There's a temporary waiting area and help will arrive to advise further. For those on Zoom, please stay on mute and with video off during the lecture. You can put questions in the chat channel at any time and they'll be answered in the Q&A session at the end. Now, looking ahead, we have our summer break, and we start again on Friday the 5th of September with a lecture called Flip It and Reverse It, Probing the Origins of Oblique Planetary Systems by Claire Davis. Or it's a bit of a tongue twister to say that. But back to tonight. Mike Edmunds is Emeritus Professor of Astrophysics at Cardiff University and the immediate past President of the Royal Astronomical Society. He's a Vice-President of the Herschel Society and has given a number of talks here, including performances of his one-man play about Newton, Sir Isaac Remembers. I only regret that we couldn't get him in character here last month when we had the talk on Robert Hooke. Over to Mike.
Well, thank you for that very warm introduction. I'm warm is probably the thing for that. And thank you everybody turning up on such a hot night. Much appreciated. We'll be going to some places rather hotter, in fact, in the talk. This is a lecture that I gave by invitation, or a version of the lecture I gave by invitation at the Royal Society of Chemistry last fall. It's the Humphry Davy Lecture, which I was very proud, I suppose you'd say, to be invited to give. The only thing I can say about it, which may happen in time, I haven't had any feedback from the chemists yet. They just sort of, I think they sort of accepted these astronomers. Anyway, there's a fair bit of speculation, I think you'll find out in this, but I think the underlying message should be clear to you. Okay. And last summer there was this wonderful exhibition of Van Gogh at the National Gallery in London. Anybody go? Yeah, it was fabulous. And I don't know if you recognise, that was one of the pictures that was there. And you could take photos. So I took photos. And it's, it's not bad as far as I can see as representation. Good old Vincent. Okay, see if I can get this thing to work then. Okay, now chemistry. I insulted my audience immediately. Chemistry, do you think of it as bangs and smells? Is that your sort of feeling from school chemistry? Okay. Well, I hope I'm going to have a big bang in this talk, boom, boom, the original thing, and there'll be a whiff of phosphine, which has got, as you know, a very bad smell. Now, my contention is, to begin with, chemistry is very simple. Didn't get me very far, that one, I have to say. Okay, but basically, and what I'm arguing in this, it's a simple argument, and therefore wrong, but it's no harm in saying it. Really, chemistry is all about. Oh dear, what did that do? That was interesting. Right, that one. Yes, that's it. It's you take some atom or molecule A, you bash it with atom or molecule B, and you get something which either then dissociates back to what you bang together, or goes on to some product C and something else. Yeah? That's chemistry. Okay? And, given that, there's the equation for how that, for the rate of that reaction. Now, I promise you this is the only equation you'll get tonight. Okay? I promise. Okay? But I wanted to show you the equation because I think it's quite interesting what it depends on. The rate of this reaction, how fast this reaction goes, how much you produce per unit time of C given A and B, is simply given by what's called the cross-section for the reaction, which I've called sigma here, which depends on the relative velocity of the particles banging together. It depends on the energy you've got involved in the collision. Okay. Now, there may be a whole lot, that's 5 university courses worth, no doubt, in understanding that cross-section. But it's just a number, eventually. It could be a variable number depending on the conditions, but it's a number that tells you how fast this reaction goes. What else is there? There's the number of A's, the density of how many A's you've got, the density of how many B's you've got, and how fast they're going together, because that determines the reaction rate, because how many you bang into each other per unit time. I'm banging more than I should do here. Right. So that's the rate of the reaction. Now, that's not a difficult equation. Okay? I hope you're happy with that. So you don't have to solve it or anything. So just agree. It's the easiest thing. But it only depends on 3 things. It depends really the densities of the reactants, this cross-section, which is chemistry, okay, and the relative velocity of the particles, which is just basically the temperature of the gas or liquid or whatever it is that's reacting. And my contention is going to be that we ought to accept that this isn't too complicated, and we ought to investigate this a lot more computationally in context of the universe. And of course, this has been done a lot. And what I'm going to talk about is looking at the results that are going to come. Most of the results come from looking at reactions like this. We're going to start off with nuclear physics and the formation of the chemical elements, and later on move on to what implications are for chemistry. Okay. So it just depends, basically, composition, density, temperature. That tells you what you're going to get out of chemical reactions. Now, the periodic table. I hope with this august audience, you'll all have met the periodic table and no doubt love it, and no doubt keep a copy under your pillow and recite it every morning as you get up. Let me just remind you that this gives you the elements, and basically all that's happening is as you go down this table, you're adding more and more protons. It's just the number of protons in a nucleus corresponds to the number of electrons in an atom that determine its chemical properties, the electrons. And each one of these has a different number of protons in the nucleus, and that builds up the periodic table. Now, I used to think this was remarkably complicated, but from viewing it from great age, I'm in fact quite surprised that it's not bigger. This is all the universe can produce by way of elements. And there are a few unstable ones or sort of on the end, but basically that's it. And that in itself, I think, is quite interesting, that there is a limited number of chemical elements in the universe. It's a finite set, and it's not that huge, actually. What you've got, 100, 120 or something. It's no more than that. A tractable problem, maybe. Okay. And for the periodic table, as you know, as I say, you're increasing the number of protons going on here, and chemistry basically is determined by the vertical columns. Things in vertical columns have similar sorts of chemistry associated with them. Okay. Now, 99% of the atoms within biological systems, all right, are carbon, hydrogen, oxygen, or nitrogen. It's interesting. Okay. Now, but more than 9, maybe even 20 other elements are essential for life. Right, first exercise, list them. Come on. Phosphorus. Sulfur. Iron. Zinc. Magnesium.
Selenium.
That's a weird one. Possibly. I'll have to think about it. Potassium, certainly. Calcium. Okay, you're doing very well. Okay. There's some of them there. Okay. And there's a good, I just put a reference here, there's a good review of hundreds of pages giving them all fairly recently. Okay. Now, CN, H, O, and N, and these other elements that are required for life were abundant on the Earth, and either in the Earth's crust or the atmosphere or the sea in the early Earth. Yeah, okay, so not surprising perhaps that that's what we're made of. It's because that's what was available. Okay, fair enough. Now, one thing interesting about those particular heavy elements there, I keep doing that, these ones, is that their ions or common compounds are soluble in water. Okay, again, oceans, you know the general story. That's okay, fine. Now, what happens around the universe, though? And we're just a little local chemical pond. What happens around the universe? How different could that be? What other kinds of chemistry and elemental mix should we be looking for? Now, I'm going to just whip through the idea of life cycle of a star. Again, you're an intelligent audience. You all know about stellar evolution and so on. Well, we heard a bit about it anyway, so I won't labour this. The sort of idea that you condense material out of the interstellar medium, you form stars, they're average stars, they're massive stars. So an average star like our sun finally becomes a red giant star, throws off the outer layers to become what's called a planetary nebulae, and the centre becomes a white dwarf star. And that's the evolution of the sun over billions of years. If you've got a massive star, it too goes through a red supergiant phase and then can explode as a supernova explosion. And then it may become either a neutron star composed completely of neutrons, or a black hole left over. Okay, general idea of how stellar evolution goes. Now, during those phases of evolution, various nuclear actions occur. The classic one in our sun is what's called the proton-proton chain, which combines, basically all it really does is take hydrogen nuclei, simplest thing, 4 hydrogen nuclei, and through various reactions forms them into helium-4, releasing some energy on the way. And it's that energy that powers our sun and keeps us warm and whatever. So in the sun, you're taking hydrogen and you're burning it, nuclear burning it, as it were, into helium-4. In slightly more massive stars, there's a similar sort of thing goes on, which again is just basically taking protons and processing them into helium, but it does by a sort of catalytic cycle. If there is some carbon or not oxygen nuclei around, it's a sort of catalytic cycle where you combine things and go round and round the cycle. What you're doing is pumping in hydrogen and pulling out helium, basically. But the amount of carbon, oxygen, and nitrogen remains pretty constant. But what this does, in fact, is if there is some oxygen or carbon around, it processes it into nitrogen. In other words, if you start doing this in a star, if it's got carbon and oxygen in it, it will eventually process it basically into nitrogen. And that's where most of your nitrogen comes from. As you know, for life, nitrogen is quite an important element. Okay, and that's where your nitrogen comes from, basically, from that sort of cycle. If you get denser and hotter than that, you can persuade 3 helium nuclei, here, here, and here, to fuse into a carbon-12 nucleus. So-called triple alpha reaction, because the helium is particles known as an alpha particle. If you can get them dense enough, they'll form a very short-lived beryllium-8 state, and you can bash, if you're quick enough, you can bash another helium in and produce carbon-12. And if you bash another helium into a carbon-12, what will you get? Oxygen. That's right. Okay, and you do that as well in things. So a lot of your carbon and oxygen will have come from that sort of reaction. Okay. Now, the majority of elements, however, the heavier elements, as I've mentioned, will be formed in supernova explosions. This is the supernova explosion you may remember, or at least have heard about anyway, occurred on February the 24th, 1987. This was in the southern hemisphere when in the Magellanic Clouds, a star, there it is seen before it blew up, and here it is afterwards, blew up as a supernova explosion. I was really cross because I left Australia 3 weeks before this. I was on an observing trip and left 3 weeks before this blew up. So there we are.
I saw it.
You saw it. Now, tell us about it.
Well, we had an upset breakfast because John Danziger, who you know, came up to me and said, "There's slight disruption to our observing programme. There's been a supernova." I said, "Oh yeah, I knew he was interested in supernova." He said, "In the Magellanic Cloud." And I thought, "Oh gosh, that's our observing program gone down the drain." So we had to observe the supernova every night while we were on the observatory on the mountain. But it's quite spectacular, real naked eye event.
Yeah. Okay. Well.
Can I ask how big it was?
Well, it was just.
It's bright. It's bright. It's not big. It's just a point source.
It took quite a number of years for it the memory to be big enough to.
In the sky? Because the sun.
It just looks like a star. Looks like a star. Nothing more. Okay. And here's one that went off. I prepared some time ago in 1054. These Crab supernova. Now, the thing about these supernovae is, as I say, there's an explosion that it gets very hot, very dense. Whole load of nuclear reactions go on. But the thing exploding delivers the elements that are formed out into the interstellar medium. It's a great thing about it. It actually makes them and then delivers them. It's better than Amazon, basically. Okay. The first 3 minutes of the universe level, all the chemical elements we have, apart from helium, hydrogen, a little smidge of lithium, beryllium, all come after the Big Bang. Okay? They're all being produced in the sort of scenarios I've already been talking about: stellar evolution, supernova explosions, stars, binary systems, supernova explosions, etc. That's where our chemical elements come from. The only exception to that, as I say, is the first 3 minutes of the Big Bang, where you produce hydrogen, some helium, and a tiny bit of lithium and beryllium. Everything else has been made subsequently. Okay. Now, here's a sort of plot of the current composition of the solar system. It's on one of these logarithmic scales. I expect you're used to these logarithmic scales by now. It's factors of 10 up here. You get 10, another 10, another 10, factor 10, factor 10, factor 10, factor 10. It's just a way of compressing data to be plotted. And here's carbon, oxygen, and nitrogen. We were talking about synthesizing those in stars. And here's the rest of the chemical elements, with how abundant they are in our own solar system. And what you notice from what we can tell you about this plot here is that this lot around the iron peak, in other words, stuff like iron, cobalt, nickel, it's called the iron peak, and it basically forms in supernova explosions. If you boil up, you get a big saucepan, put stuff in there, get it hot and dense as you like, you'll get to some sort of equilibrium state. And what you'll find in there is iron and cobalt and nickel and so on. So that's where that lot come from being very hot and very dense in an explosion. All the elements beyond that in the periodic table are formed by taking those peak elements, basically, and irradiating them hard with neutrons. Because in equilibrium terms, if you just cook things up, they wouldn't go any further. You have to have a different process that pushes down the periodic table, and that is neutron addition. A high flux of neutrons bashing into these nuclei will push them down into the elements beyond the iron peak. Now, that neutron addition process was largely thought to be possibly occur in supernovae, and probably it still does. Just to give that again, here's the number of protons and number of neutrons in the nucleus. You can find this on the web if you want to. You can see these are the stable elements in the middle, those dark blue ones. And that's it, basically. You push with neutron flux down here to synthesize the ones that are further down. And eventually it won't work any further. As you can see, you just sort of run out. But each of those little places there, if you imagine you've got some nucleus in there with some Z, which is the number of protons, N, the number of neutrons, and there are all sorts of processes. You can bash it with neutrons, you can bash it with radiation in supernovae and so on, and there are various processes that can go on, and those have been I won't say completely calculated these days, but there are very extensive calculations looking at those sort of reactions to see what sort of abundances of the nuclei you would get by doing that things, and they agree pretty well with what we see. And so here's our periodic table again, and I love this picture. You can find this on the web if you want to, because it shows the periodic table. Yes, you recognize the periodic table again? Yeah? But this one is quite clever because it shows you where the element was formed. Okay, it's key to show where it's formed. So hydrogen up there, it's Big Bang. Helium is basically Big Bang. There's a little bit of other stuff in there as well. Exploding massive stars. There we are, this lot. I told you about that lot. Okay, that's mainly exploding stars. Exploding white dwarfs, that gives some of the iron group too. What else have we got? This lot, though, is largely by neutron addition. Now, I'm sure you'll be interested in one of those, which is what? Gold. I knew you'd know that one. Okay, now gold is interesting because it looks as though it's entirely made by neutron addition processes. And until a few years ago, as I say, one began to think that was mainly some sort of neutron irradiation in supernovae. But the current model is that merging neutron stars are where this huge flux of neutrons occurs. Now, I don't know if you've been following, but you may remember in 2015, the first detection was made of gravitational radiation from the universe, okay, in these big gravitational wave detectors in the United States. And basically what happens is you can get two stars which are endpoints of stellar evolution and are basically extremely dense and formed mainly just of neutrons. And you often have binary systems of these, and now let's see if I can get this to work. There we are. Okay. There we are, two neutron stars in orbit each other. This is about real time. In other words, these are going around, it's an old system, and they're gradually getting closer and closer and closer. You can see the gravitational radiation coming off, and as the gravitational radiation comes off, it's radiating away the energy. They're getting closer and closer and closer and closer together, and it sort of gets of radiation coming out until... Okay, and in that final moment, the neutron fluxes will be horrendous, okay? And it's probably there, that flux into the medium surrounding this neutron star, that is where you're going to synthesize most of these elements, like gold being a good example. Okay, so that stuff goes off, and it goes off into the interstellar medium. I'll take more questions at the end. It goes off into the interstellar medium. And of course, then will subsequently collapse into new stars. It will suddenly be formed into new stars, into planetary systems and so on. We'll try and follow that process a bit. And these are just nice pictures so that you can see the what do they call it? The hand of God or something. Hand of creation, okay. And it's a rather nice near-infrared image there, which can see through a lot of that dust. They're beautiful images, aren't they? Okay. Now, so the stuff is coming out of the sources, either the supernovae or these combining neutron stars or whatever. What happens to it? It goes off into the interstellar medium. So you have the supernova explosion delivering stuff, and stars will also have winds off their surface, streaming stuff off, so that will go into the interstellar medium. In the interstellar medium, there are clouds, there are random motions, they'll be moving around and bashing into each other like a sort of giant teaspoon stirring things. In our own galaxies, there's differential rotation. In other words, the stuff near the center goes around faster than the outer stuff. And so if you create stuff here and move it out, this will tend to smear things around. You get smearing effects. And I looked at this some time ago. I published a paper in some time ago, concluding that, in fact, in our own galaxy, the interstellar medium locally would be well mixed. In other words, this stuff would mix quite quickly into the interstellar medium. But you could get a large-scale effect from the centre to the edge. There could be a difference, because if you've got a lot more going on here than the outside, that could survive these mixing processes. But locally, it would be well mixed. And I was delighted to hear a couple of years ago this quote, the interstellar medium metals are consistent with a local ISM, interstellar medium, that is well mixed and chemically homogeneous. I told you so. Thank you. So, locally, it's fairly homogeneous. So, you may wonder, why am I saying that? Because that sounds rather boring if it's all mixed in and homogeneous. I think the interesting thing comes later, and that's the thing, it's when things begin to separate out again. The factories sort of deliver, and it's fairly homogeneous. So what happens later that's important? So, you're going to build up of abundance of elements with time. I'm going to show a horrendous graph now, okay? But it's such a lovely one that I can't resist doing it. This is a picture of the iron abundance in the universe, and this again, it's on a logarithmic scale. If this is the sun, so there's sort of solar iron abundance, that's twice solar, 3 times solar. Here's a 10th solar, here's a 100th solar. Okay? And here's the age going back from our age now back to the beginning of the universe. 13.8, 13.4? 13.8, do you? Right, 13.8 billion years ago. And here are measurements. These are actual measurements of metallicity correlated with the age of the source that's being looked at. The object's being looked at. So there's a very simple build-up of these heavy elements with time. And if I put that line in there, that fits pretty well, doesn't it? Okay? Now, those of you who are mathematically inclined, one of you at least, okay, Bob, that's just a linear model. It's just simply a linear increase with time. Just things build up linearly with time. And it doesn't fit badly at all. So you go from the age of the universe up to the present time, building up the amount of heavy elements in the universe. And but more recently, here's one from last year. That's an observation of a galaxy at a redshift of 10, where they can actually get the abundance of it. You can see it fits very well there. There's the sun. And there are other objects around us that haven't really done much. They haven't followed this general trend. Here's a galaxy called Zwicky 18, which I observed many years ago, and that has a very low abundance, in fact. It's just sat there. The stars haven't really got going. They just sit there in this galaxy, haven't really done much. It's a quiet place. But otherwise, most of the stuff is following some sort of evolution with time. Just to show you that high redshift galaxy, this is, for aficionados. I couldn't resist it. This is a picture of the observed wavelength. There's a line in the spectrum, which is a line of oxygen, and its rest wavelength is 0.5 of a micron. All right? If you observe it with the Webb Space Telescope, the observed wavelength is 5.59 microns. Factor of 10? Yeah? So if you plot that in, Z equals 5.5, that's the redshift at minus 0.5, gives you a redshift of 10.2. I think it's amazing. You can see, here's a source where you can see this galaxy is at a redshift of 10, and you can measure the chemical composition of it now. Amazing. And, well, I enjoyed it anyway. Right. Okay. Now, let's get back to some more looking for what I would call chemistry rather than the abundance of necessarily the elements themselves. I couldn't resist this picture. Curiosity rover on Mars. There's obviously been a 4x4 driven through there. Recently, they found in the mudstones on Mars these compounds. Okay, C10H3. They look like this. They're just linear chains of what you call a linear chain hydrocarbon. Carbon, hydrogen, carbon joined together, hydrogen sticking out the side. We're beginning to get into chemistry now, okay? I think that's interesting. Okay, it's very simple chemistry, but, you're getting up to quite sophisticated molecules there. And those are, easily observed now on the surface of Mars. What about this? Where's this? Jupiter, big red spot. And the clouds of Jupiter, I think, are extraordinary. And I'm going to show you a quick video. I can't resist this one. This is from way back in '79, this video. But look at this. As the probe gets in, look at the clouds, the whirls, what chemistry is going on in that sort of thing. And if we look closely at the big red spot there, probably that's red because of a compound known as ammonium hydrosulfide, if it's been treated with a bit of radiation. So there's ammonium hydrosulfide, NH4SH. That's probably what gives the red colour to the Jupiter's red spot. Elementary chemistry so far, okay. Titan, which is a moon of what?
Saturn.
You all agree? Yeah, okay. And there was a fine mission to it a few years ago. There's a picture of the surface. It's again extraordinary to see pictures of the surface of these things. Mainly ammonia around on there. Temperature, quite cold. Much colder than here. Okay, 94 degrees absolute. Dominated probably by ammonia chemistry. Venus. Now, I mentioned this one because I mentioned that talk about phosphine a little bit. Well, phosphine is the sort of analogous molecule to ammonia, but with a phosphorus instead of the nitrogen. With a phosphorus instead of the nitrogen. There's its sort of structure. And there was a claim last year before, a couple of years ago, a few years ago, that they discovered phosphine in the atmosphere of Venus, and they couldn't think of any other way it could have been made but by some biological process. Well, I'm sure there are other processes that made it, but it created some interest. And I mentioned phosphine because phosphine was investigated by our friend Humphry Davy, whose lecture this is, okay? He investigated that around 1818, just before this society was, before the Bath Society was founded, and he basically got the structure of it, but it wasn't actually discovered by Davy, it was actually discovered by a Frenchman, I have to admit. Okay, I'll admit on his behalf, in 1783. Anyway, that's the link with Davy. Now, what about Europa? Europa is a moon of... You're doing very well, keep going. Jupiter, okay. And as many of you will know, it's one of the places where chemistry, who knows how advanced, really could be very, very interesting. Because underneath its frozen surface, it's quite possible... Oops, I keep doing that. Its frozen surface, there is actually a sea, an ocean underneath the surface here. Water ocean, who knows what exactly it would be, but the moon itself will be kept quite warm by the gravitational effects, the tidal gravitational effects of Jupiter. So there may well be a warm ocean full of nice goodies underneath its surface. So, if you're doing chemistry, a pot boiling is an interesting place to look. And as you may have known, last October, there was a space mission launched called Europa Clipper, which by 2031, does seem quite a long time ago for some of us, I'm just 2031, might get there. And this space probe will orbit within about 25 kilometers of the surface of Europa, and will be looking to investigate with remote sensing the extent of the ocean underneath, and I assume it will also cover, I believe it does carry, some sensing, chemical sensing, in case there's sort of vents through that may have some chemicals coming through from the ocean underneath. That will be absolutely fascinating to see what might be there. Now, this idea of molecules and being used to detect life is really what the rest of the talk is about. I'm sure you've heard of this idea of biomarkers, they're sometimes called, or biosignatures. If we look at planets in our solar system or at planets around other stars, exoplanets, which I'll talk about in a minute, one of the things you can try and do is look for compounds and see if you can find compounds which you think are associated with life. Now, whether they are associated with some sort of life is the big if, and that's a question we've really got to hammer away at in a few minutes. But the idea is you could look for things like oxygen, ozone, carbon monoxide, carbon dioxide, and so on, and speculate as to whether some strange mix of these things imply that there's something biological producing these gases. And if you've been listening to over the recent news, you'll have seen various people claiming various things, which I'd say beware. Okay. Now, this has become so much more interesting, obviously because of space flight to nearby planets, in the solar system, but also because now we do know that there are planets around other stars, so-called exoplanets. And here, as for last October, these are a sample of planets that have been detected with their masses around other stars. I think it's a remarkable table. Already you can see, I haven't totaled these up. Well, this must be over 1,000 there, isn't it? About 1,000, 2,000, something like that. And they're different masses for planets. These are planets we know are around other stars. And what you notice is they're not all the same as Earth, okay? And the very low mass ones are very difficult to detect, so those have got to be, for the future, to be detected. But there are all sorts of masses there. And I just show again one of these silly graphs that you look at and say, oh, what the hell's that? Basically, here's a plot of the mass of the planet against the semi-major axis of the ellipse that's going round. In other words, their orbit. So 1 AU is the orbit of the Earth around the Sun. Okay, 1 AU, there we are. There's the Earth on this diagram. And these are all the ones that have already been discovered in other planetary systems. There's a sort of detection limit you have to be careful of, because things aren't sensitive enough yet to push detection of other systems back along here. But already you can see there's a fantastic range of masses and orbits and whatever among these planets going around other stars. And what I'm pleading for here really is, well, that's very interesting. And how are we going to understand the chemistry that may be going on in these systems, which are very, very different, a lot of them, than Earth-like systems? As you can see, we haven't really got down yet to discovering systems that are very much like our own solar system. There will be them there. There will be lots of them. But there are lots of other kinds of systems as well. And one of the great hopes of doing this is a thing called eclipse spectroscopy, okay? And basically it works in this way. If you've got a star that you're observing, here's the star you're observing, and you can see a planet going around it, and things are arranged such that the orbit of the planet is in the plane that you're looking at, so that sometimes the planet passes between you and this distant star, then you can watch what the light looks like when the thing's in front compared with what it looks like when the thing is behind, and you difference the two. And what is different to some extent is the light passing through the atmosphere of the planet. And from that, you can do some chemical analysis. And that's already being done. Here's a picture from the Webb, a space telescope, of an exoplanet in the WASP system. And what a lovely spectrum. What can you see? Sodium, water, carbon monoxide, carbon dioxide, sulfur dioxide. Already we're beginning to be able to determine the composition of the atmospheres of these exoplanets. Now, look at that. Does that mean life? Well, we've got to be sure, haven't we? We've got to carefully work out what's really going on here. Because, our atmosphere has water in, carbon monoxide, it has oxygen, it has sulfur dioxide, but some of our atmosphere is very much influenced by life, but not all of it. Okay. So, Here are claimed detections already in exoplanet atmospheres. The atomic species, you can get them there, I won't read them out. Those are claimed to all have been detected in spectroscopy in exoplanet atmospheres. Okay. The following molecules have all been identified in exoplanet atmospheres. It's quite an array. Okay. We're not getting up to anything very sophisticated yet, but there's plenty of chemistry there. Okay. So, very interesting. The fact that you've got any molecules at all tells you chemistry has been going on, because chemistry means combining up atoms into molecules. Yeah? And then molecules reacting with more molecules, etc. Now, what have we been talking about so far? Here's a diagram which I rather like, which I haven't seen plotted before, but there we are. It's a diagram of density in the universe against temperature in the universe. So this goes from 0 degrees Kelvin to 10 to the 10 Kelvin. 10 orders of magnitude in temperature. Here's density up the other side. That's 42 orders of magnitude up there, okay? 42 powers of 10 up there. So it's a fairly wide-ranging diagram. If you plot on here, that's where the stars lie. Here's where supernova explosions go off, up here. Here's where the Big Bang was when it was making helium, okay? Here's the sort of interstellar medium. Here's where planets lie, and you lie here. Okay? Now, what we were talking about earlier was nuclear physics, yeah? About forming the chemical elements. Well, hang on, I'll go back. Nuclear physics we were talking about before was up here. That's the sort of densities and temperatures we were talking about in supernova explosions and stars that make the chemical elements. To do the chemistry, you need to be in this sort of region of the diagram. It's where you're going to do chemistry. And there's where exoplanets are, and here's where the interstellar medium is. So this is the region we need to look at for doing chemistry. We've formed our elements up here in the nuclear processes. They've gone into the interstellar medium. They've formed into planets. They're in the interstellar medium. And the chemistry is taking place in different conditions. Okay. So you're off into the interstellar medium. Here's a nice picture of the interstellar medium. And here are molecules that have been detected in the interstellar medium, just between the stars. Okay, here's some of the molecules. You can do it at particularly at radio wavelengths, you can do this quite well. So there's some nice molecules from the interstellar medium. Nice chemistry there. And if you want ones with a little bit more complicated, those have all been detected in the interstellar medium. Do you get the feeling of chemistry beginning to build up here? Okay. Now, I want to move on to this formation of planetary systems because I think this is where things may get quite interesting. You're able now to map actual planetary systems in formation. This is from the ALMA, the Atacama Large Millimeter Array in Chile, where at a millimeter wave radio wavelengths, they've mapped here a protoplanetary disk. This is about 200 astronomical units across. Remember that sort of, I'd say 1 astronomical unit is Earth to Sun. Okay, is it 2? Pluto is 39 astronomical units or something like that. So this is, that's Pluto out there, whatever, it's that sort of size. You can actually see on this dark rings where probably planets are already forming, and it sort of sucked some of the material out. And in protoplanetary disks, again, molecules have been detected. Here are from 2023, some of the molecules that have been detected in protoplanetary disks. Okay, interesting ones there. Now, what happens in a protoplanetary disk? You really need another talk on this by some expert in star formation, but all I'm really saying, and I'm going to, I suppose I better not move away too much from this. Okay, here's a protoplanetary disk. It's not very easy to see here. Basically, this is what's going to come out, a planetary system like our own, say. Here's the sun, and here are the planets forming out as you go out. And the disk is collapsing, the sun is forming, And in the outer regions, it's quite cool to begin with. And you get condensation, you get ices, you get mixing around, but the sun is forming and the sun is heating things up on this internal part and heating the disk. And things are moving around the disk and being evaporated and condensing and all the rest of it. And I believe that it's here that the really interesting stuff is happening. Okay, we have a pretty good, well-mixed interstellar medium. But when planets form, in the different ways they form, the different planetary systems, the different planetary disks, I think in this scenario, things can get much more complicated. And in particular, you get mixing on all scales, and you get separation of stuff on scales. You can see the separation in our own solar system, because the inner planets are rocky, and the outer planets are gaseous. Okay, because the gases got blown out, as it were, or pushed out, basically, to the outer parts of the solar system. So I think you're getting mixing, you get separation, and you get sort of compartmentalization on all different scales. You know, this planet will form in some conditions, that planet will form in different conditions, with different chemistries, different elements, different mixes of elements. Okay. So, don't worry about that, right. So, what variation in physical and chemical conditions are there among these forming planetary systems? In exoplanets, well, I've just talked about that. You can think of all these different conditions that might occur in these different planetary formations. What conditions are different between the different moons of exoplanets? Okay. There's the interstellar medium itself. We've already seen it has complex molecules in. How far can that go? How far can chemistry between the stars go? I haven't really thought this through, really, but you've heard about interstellar dust, interstellar grains, you know, small particulate matter in between the stars. Perhaps a particle of a micron size. Over age of a galaxy, what chemistry can actually go on within a micron-sized grain if you leave it long enough? Heat it occasionally, bash a few cosmic rays into it, a few high-energy photons. Nobody knows, it hasn't been calculated, but it might be a very interesting thing to ask. So, we also know that apart from those other things, there are free-floating planets. Some recent calculations done this year, or published this year, suggest that when you form one of these planetary systems, 40% to 80% of planets get flung out and don't stay in the system. So, not only are there planetary systems out there, there's all these planets milling around everywhere that have been flung out of their formation processes. Okay, they're not near a star, because they've been flung out, but what goes on them? What chemistry? What processes? Because, as you know from the Earth is hot. Why is the Earth hot under your feet? Why? Yeah, basically. For Jupiter, it's interesting. Jupiter has some radioactivity, but some it's just because it's still contracting from when it was formed. The contraction still releases heat on Jupiter. But for Earth, radioactive elements gradually decay have heated it up. So you could have something in space wandering around, not near a star, but still hot because of radioactivity in its insides. So what sort of chemistry goes on there, just below the surface where it's warm? Okay. What other bits and pieces? These things have asteroids, comets, God knows what. Each of these systems have all sorts of stuff. And you may have heard of this thing. How would you pronounce that? Again? What's more? Yeah, I'd just like to hear you pronounce it. I don't know how to pronounce it properly. But this thing that wandered through the solar system a few years ago, it's an artist impression, unfortunately. I'd love to have taken a picture, but it's an artist impression. This funny-shaped lump of rock, which they think is probably an asteroid or something, from some other completely different planetary system. Now, obviously, if one of these comes by again, we've got to send a mission to it fast and find out what it's made of and what's on there and so on. Okay. So, what I'm going to show now is a diagram that appeared in Nature last year, I suppose, remember that the formation of Earth was about 4.5 billion years ago. Compare that with 13.8 billion, or 13.4, whichever, 13.8 we decided, didn't we? For the age of the universe, okay? And what this diagram shows, they've looked at genetics, and by doing genetic tracing and so on, they can reckon that already by about 4.2 billion years ago, which is only a short time after the formation of the Earth, biochemistry was going. This is a part of a diagram of modern biological reactions, just let's put it that way. And they reckon the heavy lined-in ones here were already going by 4.2 billion years ago. Right? So whatever happened on Earth to produce life happened quickly and continued. On Earth, we know that there are various things going on. Well, it's clear that on Earth, at least, a complex chemical network can build up within 400 million years. That's short on a cosmic timescale. You can build up a big chemical network. And also on Earth, what we know from the way Earth's gone is, it gets shocks occasionally. The dinosaurs got done by a big, well, no, was it an asteroid, essentially, impact? Okay, probably. Or other ones are caused by volcanic activity. So you have a melting pot, say, on our Earth of these chemical reactions, and you kick it every so often just to stir it and get things going. Presumably, again, the same thing happens on planets or in space or whatever. There's you've got chemical reaction, and you bash it occasionally to encourage things to happen. So, what am I trying to say? Well, to paraphrase P.C.W. Davies, great popularizer and physicist too, actually, it's difficult to know what to look for when you don't know what you're looking for. I'm saying, look, I want to look at this chemistry. I want to know what's going on out there. But what do I look for? I'm not quite sure yet. Okay. One thing you could look for is a thing called stoichiometric autocatalysis, which, of course, you're all very familiar with. Now, what does these awful words mean? All it means is you've got a chemical reaction where if you produce something, I go A plus B and I get C, and then C makes the reaction go faster. It acts as a catalyst, making the reaction go faster. So the thing you're producing helps you produce more of it. It's a sort of non-linear effect. It's, to those that hath shall more be given. It's almost religious in its efficacy. Okay. So you can look at elements that have chemistry that is non-linear, that if you start something off, it will go further. And so it's a theory of chemical systems that can make more of themselves, basically. Now, all those elements in the periodic table, have compounds that undergo stoichiometric autocatalyses. These are all good at making that sort of thing. Now, CNO, you've got those at CNO, we knew about those, organic chemistry, but all these others can do some of those sorts of reactions. So don't limit yourself to organic chemistry when we're talking about this. Think carefully about other chemistries might be possible. So, I'm trying to say, well, look, in the universe, when we're talking about chemistry, how many molecules? How many reactions? What's the size? What's the size of this problem we're trying to wrestle with? Well, I want you to think of something called chemical space. I don't know if this will come up in the press before too long. Is the idea of chemical space, which is, if you imagine we've got three-dimensional space, up, down, sideways. Okay. I want you to imagine a sort of space where we have number of carbon atoms along that way, number of nitrogen atoms along that way, number of iron atoms along that way, and so on. And what chemicals could you build up in that space? Be a multi-dimensional space because of all the different elements. But can you imagine that sort of thing? It's a sort of playground of all the possible things you could make up using all the different elements in different combinations. Call that chemical space. Now, asking how many molecules there are, I'm going to get some silly numbers now. A few years ago, these guys, Kirkpatrick et al., worked out if there were less than 50 atomic mass units, that's less than 500 times the mass of hydrogen atom, and you took carbon, nitrogen, oxygen, and hydrogen, you could make 10 to the 60 different compounds. Sounds a bit complicated, but obviously, okay. Keep going. You could say it's the number of molecules is infinite, because you've got a chain of molecules, you always add another element on the chain, but let's not worry about that. Okay. What I'm saying is, I suspect, I can't prove this, but I suspect others suspect too, physical laws, laws of physics, and the way the evolution of chemistry must go, if you've got chemical systems evolving, it must severely limit what regions of chemical space are actually populated. In other words, there must be sort of islands in this chemical space that you can have lots of reactions going on and stable compounds and so on. It's not uniformly populated. There are places that show interesting chemistry and other places that aren't interesting at all. But of course, even if those are only severely limited, there's still a lot to be explored. There's an editorial in this Journal of Chemical Information and Modelling last year suggested the number of possible molecular forms was something between 10 to the 16 and 10 to the 200. Now, those are scary numbers, okay? Seeing as the number of atoms in the observable universe is only 10 to the 80, I think you're going to have trouble making the 10 to the 200 of them. Okay, it's large numbers, but I don't think, I'm suggesting it's not intractable. Again, estimates maybe 1 billion molecules with less than 100 carbon atoms. It's big, it's not impossible. Okay. Already it's known that about 219 million chemical compounds are known. They're on the chemical abstract. So you can look up about 200 million actual chemicals that we know about. Now, is that a big number, or is it or not? It's quite a big number, but given modern computing and AI and stuff, I don't think it's unreasonable to assume that you could put together a program which will look at that sort of number of possible chemical reactions. It have to be carefully written, and you'd have to do very clever things about calculating your reaction rates and so on, but I don't think it's impossible. And one thing that has happened recently is that the big drug companies have put a lot of money into theoretical chemistry to look at structure of molecules for drug design. Okay, and you may have known about, is it on here? Yeah. AlphaFold, have you heard of AlphaFold? A Nobel Prize was awarded, I think, last year, for a program that could work out how proteins folded, a theoretical program. Now, if you've got the drug companies putting money in, they're going to put in far more money than the scientists can, the sort of astronomers can put in and whatever. But if they produce programs they will share about molecular design, I think there's a real possibility that you could actually begin to do some computing of this chemical space, to explore the chemical space and work out in these different conditions, different planets, different whatever scenarios, what sort of chemistry goes on, what happens, just to get some ideas, what simplifying ideas there, where's their stability, where isn't there, and so on. So, I want that exploration of chemical networks. Look at chemical space, explore it. And why is it needed? Well, first thing we've talked about already, we've got to have some way of working out whether chemicals we see in the atmospheres of exoplanets come from biological sources or from some other source. Just ordinary chemistry without there being any sort of lifelike thing there. We need to be able to differentiate between these two. Okay, it's very important if we're going to begin to claim that there's some sort of life there. So, and I want to say we could explore the richness and limits of structure of chemical space. And as I say, there's something like 10 to the 23 or 10 to the 24 exoplanets out there. That's a hell of a lot of chemical experiments. And I'd like to, think we could begin to think about what could happen. Plus all the moons, asteroids, all the rest of it. Okay. So chemistry exo-experiments are going on. If we're going to explore them, I think we need to do some theoretical work to be able to try and understand what might be going on. Okay, it's a real challenge to chemistry. I know, so I was doing this to the Royal Society of Chemistry, and they remain remarkably quiet at this point. Very difficult, but I believe it's very worthwhile. Okay, so I'm looking at a vast computational set of experiments, really. Analogous to those of you who know about it, the Miller-Urey experiments, which were done in the 1950s, where they just put some elementary chemicals in a glass thing, ran some electric sparks through it, real Frankenstein stuff, and analysed what they got out. And they got all sorts of things, amino acids, all sorts of compounds. I'm saying do that computationally and see what happens. Okay. Begin with a carefully selected region of chemical space. Don't try and do everything, okay? So it'll be some, chemical reaction that works like this you've got to do. Okay. Now, to finish off, I've got 5 minutes, all right? 5 last minutes. Yeah, I think I have assent. Okay, Tony?
Yes.
There was an interesting paper, which I did. I don't know if anybody else has picked this up. I'll see if anybody else in the room has picked it up. Called Defining Life in the Universe. Have you ever heard of this paper, anybody? No? Okay. Well, I think it's quite an important paper. It may be one of these sleeper ones that you'll hear about in years to come. It's only about 5 years ago. And you notice they spelt life in a slightly unusual way. And the reason was that in a way they're talking about what I'm talking about, saying, look, when you look at the universe in chemical terms, don't be too blinkered that life as we know it is what we should necessarily be looking for. Okay? The thing's much, much bigger than that. Okay? And they're saying the time life, this term, can be applied to as yet undiscovered or perhaps uninvented systems that exist at a myriad scales across the universe. Okay? Now, what you can imagine is the following. They drew this Venn diagram, basically. Can you imagine? I talked about this chemical space, right? Here's a reduced form of that chemical space, okay, with whatever, all these different compounds and reactions going on in there. Now, suppose there's a sort of subset of that sort of have dissipation, which means that there's a flow of energy going through things. And I suppose from our experience of biology, we like the idea of energy flow to drive things. So if something interesting is going on, perhaps there's some flow of energy going on, okay? Autocatalysis, which we talked about, okay, the idea of things can speed up their own reactions, speed up their own growth, and hence get more complicated quickly. So that might be interesting to have. There's a thing called homeostasis, which means that you've got the reactions themselves interact in such a way that they give them some control over their environment. Now, it's a bit difficult to sort of put that into words. Basically, it would be something like, suppose you heat up a set of reactions, the environment gets hotter. And these reactions react in such a way as to cool things down by some way. It favours paths that cools things down. That would be a homeostasis. It's sort of something almost beginning to control its environment. And then there's possibility of information processing. And I won't go into that, but I mean, there could be some information processing involved in these reactions. Now, if you do that lot, then at the intersection of that lot is what you'd call life. Something interesting happening in these chemical reactions. And of course, our own life might be some tiny little region within that. And I'm interested, as it were, to say, well, look, what about the rest of it? Or even this bit, or even this bit, or even this bit. They're all interesting. Just as interesting, probably, as this tiny little spot in the middle that we found ourselves in. If you look at the numbers, there are all these other possibilities. So, what I'm looking at, I suppose, is you want to find out if from this chemical reaction lot, you can get at something like sort of emerging autonomous systems, something that does this, these reactions are doing things, evolving, whatever, which in some cases you might say resembles life, but doesn't have to. Okay, now, I gather some of you, I talked to a couple of people earlier about this scientist at Cambridge, I believe, has been on the radio or on the TV very recently. And I noted this quote from him a couple of years ago. The ultimate breakthrough in exoplanetary science will be the detection of a biosignature in the atmosphere of a rocky habitable zone exoplanet. Right? That's what he said. I don't agree. Okay? Unambiguous detection. Now that is hard, but it has to be hard. Because unless you can be sure you're detecting the thing, you don't know. You haven't learnt anything unless you can do it unambiguously. Also, why habitable habit is any planet would do. I don't mind where it is. Maybe more interesting if it's not in a rocky habitable zone. Okay. And I don't want biosignatures. I want radically new chemistries. Because that's much broader and much more interesting. So I'm not a fan of it, as you can see. Okay. And of course, apart from this idea I'm having about doing calculations, the calculation will also be useful for this. What are we going to find in solar system bodies with more space flight and more detection? That's obviously fascinating still, because that's real stuff. Okay. People are talking about, you can start doing this searches very far back. As I said, chemical elements formed very soon after the Big Bang once you got the stars going. So you can go right back to near the Big Bang and start looking for life if you want to, or looking for these sort of things. Okay. So I'll leave you with this quotation, which you may know of. I think this interest in exobiology and biomarkers is fascinating and really important. And the detection of extraterrestrial life will be a major breakthrough in the history of science. But we have to be very careful that we're sure about it, and that's why I'm suggesting all this chemical investigation. And I'm saying be careful to make sure you don't get too blinkered to look for necessarily organic systems that resemble ourselves. There may be lots of interesting stuff that doesn't resemble ourselves and has lots of fascinating chemistry going on. At which point, I will dry up. Thank you.
Thank you, Mike. You've obviously got a very good reception here. We'll take questions in the room to start with, and then I'll check to see if there are any on the chat channel. Because we've got an online audience of about 17, I think, it's very important that you talk into the microphone. Actually, it's best to hold the microphone right up like this. You can hear how that sounds better. Okay, I'll start in the front.
Well, I did ask you this before in a slightly different form. 65 million years ago, a lump of rock a few kilometres across hit our planet, and it did a lot of damage. One of your slides shows the vast number of species, but basically it took the dinosaurs to where they could not survive any longer. And it made room for us. Now, we know almost nothing about this asteroid, apart from some basic facts. But one thing we do know is it contained a lot of iridium.
Iridium. Yeah.
A lot of iridium.
Yeah,
because,
okay. And you're asking why? What does it mean?
Well, it's an example of one of your chemistries.
Yeah,
that produced...
That's right. Our solar system had a pocket in which was different from the gross composition.
Yeah.
So there are these regions. Absolutely. Thank you. Yeah. So that's the sort of thing I'm saying. There is, the planetary formation system is when planets form in star formation and so on. That's probably where these various anomalies get introduced. That's probably there, and they could be big anomalies. Yeah.
Yeah.
Yeah. Thank you.
Thank you. Thanks so much, Mike. I have two questions. One relates to the physics of what you started off with, and then moving on to chemistry, biology, etc. So to start with, when you talked about the heavier elements forming with the neutrons clashing into the protons, My question is, did the neutrons merge with the protons to create...
No, you've got a collection which is a nucleus. It's got neutrons and protons in. You can add more neutrons into that.
Yes.
And so it'll grow.
Yes.
Right? But then you're getting a nucleus which has got a lot of neutrons in, not many protons. And what will happen is some of the neutrons will then decay.
Right.
To form protons.
I see.
So, and it will gradually then move along
right.
to higher and higher atomic
numbers. But the neutrons have the same mass as the protons.
Approximately. They're not exactly the same.
Right.
And the neutron on its own is an unstable particle.
Right. So it has the potential to form another proton.
Yeah.
Right. So moving on to the later part, when you talked about the biological evolution in the universe. So I just want to...
Chemical evolution.
Okay, chemical evolution.
Which might include
biology, biological stuff. The Vedas have talked about the yugas. Yugas are ages, basically. So the universe actually is cyclical, and it goes through these ages. So the first yuga is when the physical formation is happening. The second yuga is when life evolves, and then the third and fourth yugas, life evolves, and then everything comes to an end because... and then it restarts.
Given recent developments in America, that may well be occurring.
Yes, but yes, I haven't finished. So
excuse me, we need questions.
The evolution, I'm talking about what's in the Vedas.
Yes, can you put a question, please?
And my brain needs to work.
Okay, thank you. Okay. Any other questions, please? We have questions, not alternative lectures.
Yes, there's one at the back there.
Hello. You had a slide earlier with the chemical composition of the universe, and you had kind of carbon, nitrogen, and neon at the highest predominance, and then uranium at the lowest. I didn't see hydrogen in that chart. Or maybe I missed it.
No, it would have been up off the top. That's why. It would have been off up the top. It was normalised to hydrogen, basically.
Thank you.
Fair comment. It's by far the most common element in the universe.
No questions online yet. Do any of the online...
There's one at the back.
Thanks, Professor Evans. That's a great talk. Just on the subject of dark matter, is it possible that it has a chemical composition such as like a ferrofluid, for example?
God knows, and I suspect he's the only one who does. The problem of dark energy and dark matter is when we sort of hold our heads a little bit in shame and worry about. We have no idea, as far as I can see, what dark matter really is, or what dark energy is in the universe. We can see their effects on a large scale, but only on a very large scale in cosmology. Okay, so it's not surprising we didn't notice it before. It's only when you go to very large scale measurements that you begin to see these things. And we have no idea really what the laws of dark matter might be. All we know is that dark matter does interact gravitationally with ordinary matter. And that's about it. That's what we know. We don't know whether it has a chemistry, what its equation of state is, or we have some idea, but nothing that really is particularly physical. So I rather, to some extent, I rather regard us as being at just before Newton. We know that the planets... Well, if you go back to Greece, it's almost like Greece. They know the planets have irregular orbits. Not around, they assumed it was around the Earth, a geocentric thing. So they knew the planets moved around, and they could predict very accurately how they moved around. But they had no idea why, right? And we're a little bit like that with dark matter. On the very large scale, we can see its effects, and we know what it's doing to the universe. But we've no idea why, other than that it reacts gravitationally. And that's for future research. I can't tell you any more than that.
Mike?
Hi, could I just go back to your very original equation, your one and only equation, the rate at which reactions take place?
Yes.
And on the right-hand side, you had the kind of density, velocity. But one other parameter is the cross-section.
Yes.
So if you're going to work out chemistry for fairly complex molecules,
yes,
and you're also kind of looking at collisions, reactions happening at a sort of quantum level,
yes,
how well are those cross-sections understood?
Well,
because they would obviously have an effect on the reaction rate.
This sounds like an excellent review of a grant proposal. You're absolutely right. In the thing is that, and that's a real, and that's, people spend their life trying to work out.
I should disclose some interest in that.
Okay, that's fine.
Research I did many years ago was on those cross-sections.
You'll know that, therefore, it's very, very difficult. But what I'm asking for is something a little bit simpler. I'm saying, look at all kinds of chemical reactions. So use AI if necessary to help you sift vast quantities of data. Parameterize as best you can. Okay, and you'll get some sort of empirical, well, not empirical, but some sort of guess at what is a reasonable cross-section in certain conditions for different molecules and so on. And as I say, with some of these more intricate structural prediction programs, you may be able to do even better than that in the future because you'll have, good computing. So I'm just hoping that there will be ways of having a go at predicting what those rates are, even if you can't measure them, okay? It's a big ask because you can say, well, you've got to check it. Okay, well, you can try and check it. But if you could do that, then I think to look at how the whole matrix of reactions behaves is worth doing that, even if it's a little bit iffy.
I did try all that back in the 70s.
Yeah, okay. And I might just mention, actually, I've just got one slide I didn't show, but might certainly interest you, if I may just put it up. This is some work which was reported in Nature last year. And I'm sorry about the graphics, just to remind me what it is. What they've done is they have a chemical reservoir, and they feed in chemicals. Can you see the chemicals coming in here into the reservoir, and mix it round, heat it up, and then have a mass spectrograph or something similar on the outside, or a spectrograph of some kind, to measure what's coming out. Right? And they call this the chemical computer, because what they say is we can compute what is happening to these molecules by looking at the products and varying what we put in. So you could do some sort of checks in that way. I'm saying do this theoretically, but there are people who try and do it, physically. And tie the two together, you might be able to constrain a bit the computing parameters you put in. It's all hopeful. It's all pie in the sky, but, who knows?
Right. Can I have one? In that case, as you know, there's no room. I'll come back to you for a minute. Okay, sorry.
Don't let him ask me a question. That'll be difficult. Go on.
Okay. One of the really big questions, of course, is life on Earth unique? And there are a broad spectrum of opinions because there are no data. So I think the question is a sort of rather general question. Given what we know, or what you just told us about the properties of the Earth and the chemistry, the kind of chemistry that can go on, do you see anything extraordinary about the Earth which would qualify it to be a unique place for life? And if not, isn't it clear that life will form wherever there's a supply of energy and a way of interacting with chemistry?
I look at that too. It's a very good question. It's a very fair question. The first thing would be, well, no. Why? It's a small planet and there are all these other systems. Is there anything particularly odd about this? The thing in the study of life on Earth, I think that is interesting. Number one is, if you believe it, life started very quickly, relatively. Okay, so at a molecular level. Okay, and at maybe a single-cell animal, a single-cell bacterial level. Okay, that seemed to start fairly quickly. Complex life, however, did not. To get to, I can never remember the name of the cells that are in us. Eukaryotic cells took 2 billion years at least before they were more complex cells, and your mitochondria and all the rest of it and so on formed. So there's a big block there. Why? Is there something very strange? If it starts quickly and then takes 2 billion years to get more complex, that's telling you something. Okay. And that's interesting in itself. I don't know how you feed this in. The other thing is, if you're interested in intelligence, which of course is what we're all interested in, is whether aliens knocking on the door and, whether they have two heads and whatever. Intelligence in the technological term, in other words, able to send messages, receive stars, think about the evolution of the universe, and back to the Vedas or whatever, you're talking about, people thinking about this many years ago, that's still only 20,000 at most, 20,000 years ago. Technologically, it's 2,000 years ago. And that's tiny in the time spectrum. So, what is it about the Earth? What is it about those particular events that's special? I think your general point would be, and I would agree with you, if you think about just probably some sort of self-sustaining chemical reactions that do something that allows them to propagate and form some sort of complex structure, that could be absolutely universal. Almost everywhere might do something like that, different forms in different places. How complex it can go, and whether it can go as far as intelligence, is a very, very different and open question. And that I can't, at the moment, provide any particular guidance on that. Does that make sense? Right.
That's when we go back to philosophy.
Well, and this is the problem. And science normally is based on having several cases and different things to investigate. You shouldn't do science on one thing, on one example. But the problem with Earth is, and as Bob said, we only have one example about life. And that makes it difficult to do these things.
Just a question. I'm an evolutionary biologist, and that Venn diagram you showed at the end is something that I've created in biology. Those sort of processes are going on. It's and the parallels in biology and in cosmology are really, really interesting. And I was wondering, we are fascinated by extraterrestrial life, beings, and so on, but would we even recognize it from our philosophical standpoint if we saw it? I saw a spider in my garden today, and I thought, if you were 50 times bigger than me, Bath would be terrified. So scale is really important in looking at life. How can we detect a single or small bacteria in a vast... It's just... I gave a talk many years ago, and I showed our planet over there, and I walked around the room 3 times, and I said, that's our solar system.
Yeah. I think your thing about... This is difficult stuff. But I find that if you sit in your garden, and if you're a naturalist, it's lovely. You can feel the spiders, the birds singing, and then all the rest of it. But then you realise that that's a surface layer, and beneath that there is far more in numerical terms going on in microbial life, in fungal life. Insect life and whatever. That's, if you, from the outside you say, well, that's the interesting stuff, that's the numerically interesting stuff. These humans are completely irrelevant. They're just something that big that happen to form and walk around the place. And in a way, I'm agreeing with you. You need to, maybe this is too constrictive even. We need to keep a very broad view on what it is we might be trying to find. And as you say, how would you... And a classic thing would be, well, if it was really intelligent, it certainly wouldn't want to talk to us. At the state of the world today, who the hell would want to talk to us? I don't mean that unkindly, but I think it's true.
Charles, did you have a question?
No, Bob took mine.
Talking about your sort of biosignatures, so there's a couple of things. So first of all, the autocatalysis or enzyme catalysis in our life tends to produce specific
stereoisomers, so there is a dominance of left-sided amino acids, right-sided nucleic acids and things. That's difficult to detect from space, I think, or possibly impossible, but that would be one marker. And the other one is our ability to make chains of molecules which then store information. So DNA stored as a chain, amino acids stored as a chain. And so there are many possible amino acids that could occur naturally, but we have a very small selection of those which occur very abundantly. And maybe an AI could work out how to create chains of other molecules.
If the conditions were slightly different, would you have got a different mix? Yeah, absolutely. I think that's absolutely right. And as you say, the problem is remote sensing of anything like a DNA molecule or its structure. I don't think you can do that. That's not going to be possible for a very, very long time.
Hi, thank you for a really interesting talk. I just wanted to check my understanding of something. So I knew previously that things like gold were created with two neutron stars colliding, and I'd kind of always assumed that meant that our sun came from a nebula close to two neutron stars previously exploding, but your talk talked about the way that the galaxy was rotating.
They mix it.
And it mixes it all.
But there will be places,
right?
I think you're absolutely right, where there's a neutron star goes off, and it happens that a planet forms quite near that, and therefore could have a somewhat different mix.
Right.
But on the whole, the average will be good. And I think, as I say, it's a matter of faith at the moment, is that it's in the formation of the planetary system that the separations occur. But that's just a conjecture, really.
Mm-hmm. Okay, that's all I want to check. Thank you.
Hello. Mike, thank you very much for that talk. Do you or others have any plans to put some of this material within the astronomical communities? Because it seems to me that whether it's query phosphine on Venus or the chap from Cambridge with his Earth-like planet and detection of a molecule that could be biogenic in origin, or even in Humphry Davy's day, if somebody said, oh, there's organic compound out in space, therefore it's life, it seems to me in what you said there's a need to educate some of the astronomers from now on, simply merely because the press is going to keep coming up with these tales. But I just wonder whether you've got any plans to sort of encapsulate this into some of the journals.
I did suggest to the Royal Astronomical Society last year that they set up a standing committee, and I think they've done so, to look at where claims were made and on what basis it would be fair to claim that you had done this, and to act as a sort of, if there really were if we got an alien signal or something, that they could sort of say, well, is this real? What does this mean? To give advice to governments and so on. I think astronomers are aware of these problems. But I think, I can't remember, Charles said to me earlier, it's grants. Was it you said that, Charles? I can't help feeling that, somebody's grants up for renewal and suddenly all sorts of claims are made.
Right. Well, it's 9 o'clock now, so any last question? Okay. Well, Mike has taken us through the complete story of chemicals from the Big Bang through synthesis inside stars and in the supernova and merging of neutron stars, and then finally to planetary formation and to us. So that's a pretty broad story.
It was in the title.
So let's join hands again, and thank you very much.